All right, folks, let's get started on this. This is your last set of mini lectures before your test, your lecture exam. So your lecture exam will be 15, 16, and 17, I believe. Actually, I'll check that to make sure so I don't give you false information. And looking at your syllabus, lecture exam 2 is 15 through 17. So here we go. We're going to do 17, and this is the last one before your lecture exam. All right, so you've seen this before. Just to remind you where we're going here. What we did was, we've been in the nervous system since the beginning of the semester. We're almost out of it. But here we have our senses. And then we go down and we have special senses and general senses. We finished the general senses. We did the somatic general senses and the visceral general senses. And then we did the autonomic nervous system, which was a motor nervous system. And now we're doing the special senses. All right, let's get started with the special senses. Olfaction. First one is olfaction. This is the nasal cavity, of course, and you can see the concha. Here's the superior, middle, and inferior nasal concha. That really is just anatomy here. This is your olfactory epithelium, and it's kept moist by some mucus secreting cells in the olfactory epithelium. And then here are your olfactory neurons. They are primary receptors. And if you recall what a primary receptor is, it means that the dendrite itself binds the ligand, and the ligand in this case equals an odorant. We call the molecules that bind our olfactory epithelial dendrites odorants. All right, and then these primary receptors bind the odorants, and they depolarize, and they fire, and they send their information up to the olfactory bulb up here. This is cranial nerve number 1, and it goes back to the olfactory cortex or the rhinencephalon. So this is basically the anatomy of it. Just so you know, the olfactory nerve does not go to the thalamus. It's one of the few sensory neurons that does not go to the thalamus. All right, so that's just the olfactory pathway. This is looking at more detail of the olfactory epithelium. These ligands are odorants. We call them odorants. They bind our dendrites. You can see that we have supporting cells here. Here's supporting cells. You can see that we have basal cells, and these can differentiate into neurons. Now that's going to sound weird to you, these basal cells differentiating into neurons. Probably to this point, you've always learned that that after a neuron forms, it stops going through mitosis. It goes into the G0 stage. You probably remember that from Bio 203. The G0 stage is non-mitotic. It can be permanent or temporary, and in the case of neurons, it typically is permanent. And when a neuron dies, it dies and never gets replaced. Of course, now we know that that dogma is not quite right. Now we know that there are such things as stem cells that can differentiate into neurons. So we know that's true. But it's not like replacing epithelial cells. The mitotic rate is not that great, and it does take some special chemical environment, etc. But in the olfactory epithelium, there's an exception, and that is our basal cells do differentiate and grow into new neurons that have dendrites that bind odorants, because we are constantly replacing our olfactory epithelium. Not just the epithelial cells, but the neurons as well. So there we go with that. What else? We have these olfactory glands that secrete mucus. The one thing that is necessary for us to smell something is that it must be dissolved in an aqueous solution. This mucus layer right here is the aqueous solution that these odorants become dissolved in. When your nasal cavity dries out, you lose some ability to smell, because you're not dissolving the odorant in your mucus layer or an aqueous layer. Something just came to my mind that I wanted to tell you. Oh, that's right. In the nasal cavity, we have something called the swell body. Oh, by the way, this is probably not in your book. This is not something that most anatomy and physiology books talk about. Go ahead and Google it though. Google this and you'll see that it'll tell you something similar about what I'm about to say. So you have the swell body in your nasal cavities, both nasal cavities, the left and the right um, nasal cavity. And the swell body is really a swollen. It's really a swollen vein. That's really what it is. Almost like a almost like a varicose vein of your nasal cavity, almost like that. And it they go back and forth between swelling and retracting or diminishing in size, and they swell for about 30 minutes. So the right hand nasal cavity swell body will swell for about 30 minutes, and then it'll reduce. And then the left hand nasal cavity swells for about 30 minutes. Well, what this does is when it swells, it limits the airflow through your nasal cavity, and it allows the mucus to be secreted and catch up. So now you can rehydrate your nasal cavity when the swell body is swollen. And your nasal cavities go back and forth. And by the way, when I say 30 minutes, it's probably 30 minutes to 90 minutes. And it's a range, I'm sure, from 30 minutes to an hour and a half or so. But the point is that these swell bodies swell going back and forth from right to left nasal cavity. And this prevents your nasal cavities from completely drying out. In other words, you give your nasal cavity time to catch up with the hydration of it. And then, so you're always able to have the sense of smell very efficiently in one of the nasal cavities while the other one is hydrating, and then it flips back and forth. So that's a swell body. And again, that's probably not in your book. All right, generator potentials. When we talk about generator potentials, they are the action potentials of the receptors, and in this case, the receptors are primary receptors. The receptors are right on the dendrites themselves. You can see the action potentials here. You have your odorant binding the receptor. It hit threshold right here, and you have your action potentials. This series of action potentials right here is called the generator potential. And you can see that something's going on here. Well, you really couldn't tell this in this small period of time. But the sense of smell adapts very quickly, but the receptors do not. So how can that be? These aren't phasic receptors. Let me remind you that phasic receptors adapt quickly and tonic receptors do not. So if I say that olfaction adapts quickly, but these are not phasic receptors, how can both be true? And the answer is there's central adaptation. And that means that the receptors have the same amount of sensitivity to the odorants as they always do, but centrally in the central nervous system you adapt, central adaptation. Okay. So generator potentials, the action potentials sent by these dendrites. All right, the odorants. There's a couple different ways that they act, and one way is they act through a G protein. And what happens is the odorant binds the receptor, and it activates a G protein, which turns on an enzyme called adenylate cyclase. The adenylate cyclase converts ATP into cyclic AMP. Cyclic AMP in turn goes around and opens a sodium channel. The sodium rushes in and you depolarize. So these are metabotropic receptors. Metabotropic. Let me remind you about those two words. An ionotropic compound, an ionotropic receptor, directly opens ion channels. Directly opens ion channels. Whereas metabotropic ligands and metabotropic receptors indirectly open ion channels, and sometimes the metabotropic receptors act through a G protein. Not every time, but sometimes they act through a G protein. And in this case, they do. So the odorant in the receptor is metabotropic, indirectly opens ion channels and fires the olfactory neuron. The G protein, we call it Gulf. That's G protein olfaction. That's the name of the G protein in your olfactory epithelium. It's Gulf, or G protein olfaction. This is your phospholipid bilayer of your neuron. Here's the odorant binding the receptor. Here's the activation of the G protein. Here's the G protein turning on adenylate cyclase. Here's the catalytic mechanism. Well, it's not the mechanism. Here's the catalysis of adenylate cyclase converting ATP to cyclic AMP. And then here's cyclic AMP, which is our second messenger. Remind you that the second cyclic AMP is called the second messenger. Second messenger, and then the cyclic AMP, which is the second messenger, opens the ion channels. You can see it opens sodium channels and calcium channels, and then that causes depolarization. Now, the cyclic AMP has to be broken down, and what breaks down cyclic AMP is phosphodiesterase. Cyclic AMP becomes AMP by an enzyme called phosphodiesterase. Certain drugs that affect phosphodiesterase can affect your sense of olfaction. You can have the sense of smelling something that's not really there. It's not there anymore. It's not there at all, and that could be because of a phosphodiesterase, a chemical or a drug that inhibits phosphodiesterase activity. So things that inhibit phosphodiesterase can affect your sense of smell. All right, the G protein called Gulf. These olfactory neurons right here, well, just take this box right here, and then come down here where it's blown up. So it's blown up down here. You can see that these olfactory neurons, they have a lot of what we call olfactory hairs. They are really, all they really are is the dendrites. That's all they really are. These are bipolar cells. Oh, that's something I didn't tell you. The olfactory neurons are bipolar cells. You're going to see bipolar cells again when we do the retina. These are bipolar cells. Remember, you learned 3 types of neurons a long time ago. You learned multipolar, bipolar, and unipolar, or also known as pseudounipolar. And then you also learned anaxonic neurons, and we'll talk about them when we hit the retina. So these are bipolar cells. You can see the basal cells that can differentiate and become neurons. You can see that. You can see that the neurons travel through the olfactory foramina of the cribriform plate of the ethmoid bone. You probably remember that from Bio 203. And then you can see that these olfactory neurons synapse with some different cells in the olfactory bulb. These are the cells that they synapse with: granule cells, tufted cells, and mitral cells. They do have different functions. I wasn't going to get into all the different functions of the granule cells, tufted cells, and mitral cells. I will tell you this, that the olfactory neurons are completely sensory. However, some of the signals are coming back, and what they do is they moderate the sensitivity or the likelihood of firing between the olfactory neuron and the cells in the olfactory bulb. So we can actually attenuate some smells, or we can enhance some smells, and that has everything to do with these granule cells right here and these tufted cells here. So we talk these cells can attenuate or enhance certain smells by moderating how the olfactory epithelium innervates or synapses with the mitral cells, and then the mitral cells go to the brain, and you have a sense of smell. All right, so we have those cells. This is the olfactory cortex. It's called, the olfactory cortex has an old name. It's called the rhinencephalon. Rhinencephalon. It's kind of a diffuse area of the brain, really. It's not just one area. And in fact, this is the frontal lobe right here. You can see that part of your rhinencephalon is in the frontal lobe. This is the temporal lobe right here. Part of your rhinencephalon is in the temporal lobe. So you can see that these pink circles, if that's pink to you, I guess it's pink to me, so I hope it's pink to you. These pink circles are what we're calling the olfactory cortex. And you can see that it's a diffuse area, not just one area. And in fact, part of the rhinencephalon is actually on the insula. And the insula, I told you, was for gustation. And that's true. The insula, we think gustation. But the insula, remember, is if you put your finger through the lateral fissure and you would touch the insula. So the insula is kind of this link between the temporal lobe and the parietal lobe. So it's the back of the temporal lobe, if you will. So I'm telling you that the rhinencephalon is partly in the frontal, partly in the temporal lobe, partly in the frontal lobe, and part of it's deep in the temporal lobe, close to the insula. And in fact, the sense of taste and the sense of smell are closely linked. Matter of fact, you probably know that when you have a cold, things taste differently. That's because you don't smell them normally, and they change your sense of taste. So the sense of taste and the sense of smell is closely linked. We're saying the olfactory cortex is frontal and temporal lobe here. All right. So that's the olfactory cortex. All right, let's do gustation or sense of smell. Actually, let's stop here. Let's stop here and we'll post 17.1 and I'll do 17.2 as a separate mini lecture. That's what we'll do.